All right, so for this video, we're going to talk about the kinetic molecular theory of gases and some of the gas variables and their relationships. So kinetic molecular theory is basically what it sounds like. It's kinetic, so that means motion, molecular, so motion of molecules, and theory. This is sort of like capital T theory, like a model. And it essentially explains gas behavior. It says that a couple of things, like these are some assumptions that we make about gases that allow this to make sense. We say that the particles are really small, so that the overall volume of the space they occupy in a gas is negligible. So basically you can assume that they don't have volume in and of themselves. Generally, that's true. They're in constant motion, so collisions are what cause pressure. So pressure is related to these collisions. They don't attract or repel each other. They just bounce off each other like billiard balls. That's not really true, but for the most part, their attraction is so minimal, it doesn't really matter. And that the average kinetic energy of the particles is directly proportional to the temperature in Kelvin. That's why we have to use Kelvin. So these are the assumptions that we're going to make, but let's actually look at what this theory represents. So I think we're going to use this as a lab at some point, but this is obviously a PhET simulation of a gas. And so when you think about gases, this is what I want you to think about. I want you to think about particles moving around and bouncing, and how adjusting these variables will make a difference on the gas. You'll get some more time to, if we haven't done this already, we'll definitely get to explore it. But yeah, let's take a quick look at what's happening here. So we have two different kinds of gases. There's a heavy and a light gas. And you'll notice the heavy ones are moving more slowly, but they actually still have the same kinetic energy because it's like mass, it's mass times acceleration equals the force. So the kinetic energy is still the same. Physics stuff. The lighter particles are moving faster, but they don't have as much mass. So either way, when they push up against the containers, that's what creates pressure. That's the pressure that we're reading here. And that's what this little pressure meter is reading, is every time there's a collision, it marks it as the pressure. The temperature is their average kinetic energy. So again, it's the speed, but also the mass of the particles. Doesn't really come into play too much for us, but it's good to think about. The volume looks like it's pretty fixed right now. It seems to be there's a certain amount of volume that's available at the moment. And so far we haven't played with the temperature, and we haven't removed or added any gases. So let's take a look. If you'll notice on your notes, I'm just going to keep using the simulation, but there's these variables. So we're going to play with all of these variables a little bit and just see what happens. So let's look at pressure and volume. So what happens if we change the volume? How is that going to affect the pressure? So we can actually slide this to increase or decrease the volume. So let's just take a second here. It looks like we're at about 11 or so atmospheres. Let's increase the volume. What happens to the pressure if we increase the volume? It looks like it decreases. And that would be because there's more space, so the particles don't hit the sides of the container as often. We actually can do a collision counter, and that will measure all the collisions. Kind of cool. Anyway, now let's see what happens if we shrink the volume. What's going to happen to the pressure? Okay, it's increased a lot. So what we would actually say is that pressure and volume are inversely proportional. As one increases, the other decreases. As one decreases, the other increases. I'm going to write that down on the sheet of paper. Inversely proportional. Okay. Let's take a look. Let's go back to our kind of factory settings. And let's take a look at pressure and temperature. So what happens to the pressure as temperature changes? Let's try decreasing the temperature first. So we're going to add some ice. The temperature is going down, as is the pressure. Okay, so the particles are moving more slowly. They don't hit the sides of the container as often. So it seems like if you decrease temperature, pressure also decreases. What if we increase it? pressure is rising. Again, makes more sense. All the particles are moving faster on average. They hit the sides of the container more often. So pressure and temperature are directly proportional. As one increases, so does the other. Okay, let's cool it back off again a little bit. How about pressure and moles? So that's like amount of gas. So let's say we've got this amount of gas. Let's release some of the gas. So we can actually slide this open and the gas will escape. Let's just let that go for a minute. And after we've lost gas, lost a whole bunch of gas, it looks like the pressure has decreased. What if we add some more gas? Pressure is increasing. So these are directly proportional as well. Okay, how about temperature and temperature and volume are really hard to talk about. Let's see, if we hold the pressure constant and we increase the temperature. There we go. So if we hold the pressure constant, which is kind of tricky to do, but we can kind of pretend that we can. If we increase the temperature, it looks like the volume decreased. And if we decrease the temperature, it looks like the volume is also decreasing. So pressure and temperature must be also directly proportional. Directly and indirectly or inversely proportional, it's exactly what it sounds like. It's, as one increases, does the other one increase or decrease? If they're the same, it's direct. If it's opposite, then it's inverse. Okay. How about volume and moles? So again, we're going to hold pressure the same. What happens to the volume if we decrease the number of moles? It starts to shrink. Oops, we close that container. And if we increase the number of moles, it increases. So also directly proportional. So these are the observations that we would make about moles, pressure, volume, and temperature. Those are the four gas law. These are the four variables that affect gas laws. So let's go back to our notes here, and we'll see when we put these all together what happens. If we take this data, this information, these ideas of these relationships, and you guys can jot this all down, we end up with these formulas. So in these situations, it's kind of like what we just went over. P1 and V1 are representative of the original pressure and volume, and P2 and V2 are the new pressure and volume. They're all equal to each other, but there is like a change. If it's inversely proportional, you end up multiplying the variables. If it's directly, you end up dividing. But we end up with, these are individual gas laws. And when we use the word law in chemistry, in science, often we're referring to a mathematical equation. Okay, so P is pressure, V is volume, T is temperature, N is moles, and there you go. So these are all of the possible relationships that we can think about in terms of gases and how they react to each other. And again, that model, I hope, was really helpful with that. If we take all of these and mathematically shove them all together, just add them all up, you are going to end up with this particular formula. This is called the combined gas law. And these are all really useful for problems where you're dealing with a situation where you know 2 or 3 or 4 variables, and then you're changing them and you want to calculate the new status quo. This is like adjusting for change, which is exactly kind of what we were doing in that little demo I just did, that little video there. So let's take a look. That is the notes that you need. Let's actually see how to apply this. So I'm going to go to your unit packet here. Sorry, there's a lot of papers around here. Awesome. Okay, this is unit packet page. We're going to look at 2 and 3. And do we need to go into 4? We might check out something in 4 as well, but let's pick out a problem or two. So let's actually take a look at number 1. I like number 1, looks good. So a gas has a volume of 300 milliliters and it is at 3.9 atmospheres. So let's just draw that real quick. We've got a box, it's 300 milliliters and the pressure is 0.39 atmospheres. So there's lots of little particles in there. Okay, so we have atmospheres is pressure, milliliters is volume. So that's pretty cool. So that's some information that we need. What will its volume be if the pressure is changed to 0.66 atmospheres? So in order for this to happen, we got to think about what would happen in order to make the pressure change if all we're changing is volume. You'll notice we haven't changed moles, we haven't changed temperature. So N and T are both constant. So we're not messing with those. We're just playing with the pressure and volume. Well, in order for pressure to increase, it's inversely proportional to volume. So volume must be decreasing. So it seems like we're almost but not quite doubling, or no, slightly more than doubling. No, almost but not quite doubling the pressure. So we need to change the volume. So the new scenario, we would expect the volume to be smaller. The pressure is now going to be 0.66 atmospheres. And the volume is going to be some number of milliliters, probably less than 300, probably around 150 or so, something in that range. So because we know the relationship between the two, that they are inversely proportional, one increases, the other one decreases, we can solve for this. To solve, what I would do is find one of these equations to use. It looks like we're going to be dealing with the pressure volume one, so we're just going to use that. So I'm going to copy the equation out. Okay, so these kinds of problems, it's just asking you to identify what variables are changing and finding the correct formula to use. That's the hard part. Once you get that, it's really easy. Okay, so there's our equation. Now we just need to figure out what we're solving for. We already have, if we call this the scenario 1 and this the scenario 2, we already have P1 and V1, and we already have P2, and we're just trying to solve for V2. So let's rearrange the equation to solve for V2. We'll divide both sides by P2. So V2 is equal to P1 V1 divided by P2. And we just have to fill in the variables. So P1 is the original pressure. V1 is the original volume. And P2 is the final pressure. So the pressures are going to cancel out. We end up with milliliters as our unit, which is definitely the correct unit, because that's the unit for volume. And now we just have to solve. So that's going to be 0.39 times 300 divided by 0.66. So that's going to be 177.27, or we can just go 177. That's fine. So this is 177 milliliters, which is indeed less than kind of approximately a half of the volume, which is exactly what you'd expect. So that's kind of how we can think about this in a practical sense. You want to think about what's happening here, what numbers you might expect, and then we can, like, what you expect to happen more in a qualitative way. You know, the volume is going to decrease. That's kind of qualitative. Now, how much is it going to be decreased by? That's quantitative. That's the calculation part. Okay, so that's one of them. Let's take another. Let's take a look at another. I like number 4. It's right here. Let's do it. A gas has a volume of 4 liters at 50 degrees Celsius. What will its volume be in liters at 100 degrees Celsius? Okay, so let's think about this maybe like a balloon, right? Balloons are fun. This is a 4-liter balloon. So this is what happens first. And it is at 50 degrees Celsius. You'll notice that temperature, our moles and temperature are both constant. So we're just going to ignore that. That's why I was thinking like a balloon, because it expands, and so the pressure inside the balloon and outside the balloon should be the same the whole time. Then what's going to happen is we are increasing the temperature to 100 degrees Celsius. So here's the question. What is going to happen to the volume? Is it going to increase or decrease? If we increase the temperature, volume and temperature are directly proportional. We can actually look it up right here, which kind of makes sense. As the temperature increases, the particles move. It's going to increase the volume in order to keep the pressure the same. It's going to expand. You might have experienced this, like if you take like a water bottle outside on a hot day, it expands. And if you bring it back into air conditioning, it kind of contracts. You've probably seen this before. So it's going to expand. So the balloon is definitely going to get bigger. How much bigger? Well, it looks like we're doubling the temperature. So it would make sense that the volume should double. So we should be looking at something like 8. But let's just double check and make sure the math works. So this time we're only dealing with volume and temperature. So we are solving for volume 2. So if we multiply each side by T2, we will have our equation. That's going to be V1 T2 divided by T1 is equal to V2, which is going to be volume 1 is 4 liters. Temperature 2 is 100 degrees Celsius. Temperature 1 is 50 degrees Celsius. So 4 times 100 divided by 50 is in fact equal to 8, which is exactly what we'd expect. It's 8 liters. Now, technically, you're usually supposed to do all of this in Kelvin, but for this kind of thing, it doesn't really matter. So Celsius will work just fine. If we do it in Kelvin, I think we end up with, what's that, 273 plus 100. So that's times 4 divided. I'm just trying to see if we get the same answer. 273 plus 50. No, we don't end up with the same answer. So in this case, it's probably better just to keep it in Celsius. Makes more sense. Which is weird. Anyway, we worry about Kelvin for later. Okay, keep it in Celsius. That's good. Okay, so let's try another one. Let me call out another example. Pressure, just looking to see pressure and volume. One second here. I'm just going to pause for just a second. All right, I decided to do, we'll just do number 6, and then I think that'll be pretty good. Okay, so the gases in hairspray can are at a temperature of 27 degrees Celsius and a pressure of 204 atmospheres. If the gas in the can reach a pressure of, I had to adjust for you all, 600 or 6.12 atmospheres, the can will explode. To what temperature must the gases be raised in order for the can to explode? Assume a constant volume. Okay, so we've got a can of hairspray. The volume is going to stay the same because it's the same can. You know, it's a solid metal object. It starts off at 27 degrees Celsius and the pressure is 2.04 atmospheres. We're trying to see what will happen to get this can to explode. That's my drawing of explosion. It will explode if the can reaches 6.12 atmospheres. And we're trying to say, what will the temperature be? Okay, that's what the question is asking. So we need to think about temperature and pressure. Well, do we need to increase or decrease the temperature in order for the pressure to increase? Well, the faster the particles are moving, that's higher temperature. That means more pressure because of more collisions. So we definitely want to increase the temperature. The temperature should definitely be higher. It needs to be more than 27 degrees Celsius, which is kind of like room temperature. So basically, like do we need to put this in an oven? Can we just put this outside? Let's find out. So pressure and temperature are directly proportional. So we've got this formula here. We are solving for T2. Ooh, so we're going to do some actual math here, huh? This one's a little harder. So we end up with T2 P1 over T1 is equal to P2. And then, but we need T2. So let's multiply this side by T1 over P1, right? Both sides by T1 over P1. Cancels that out, cancels that out. So T2 is going to be equal to P2 times T1 divided by P1. So pressure 2 is 6.12 atmospheres. So that was just some algebra there. Hopefully, hopefully you got that. Temperature 1 is 27 degrees Celsius, and we're going to divide that by pressure 1, which is 2.04 atmospheres. So atmospheres cancel, degrees Celsius is what we're looking for. And yeah, so now we just have to do the math. So 6.1, oops, some of the calculator sometimes, man. The 6 button on this calculator drives me up the wall. Looks like we need to get up to 81 degrees Celsius as our answer, which is not outside. Even on summer, like we maybe get up to like 44 or 45, like at the absolute most in degrees Fahrenheit or Celsius. So you would probably need to throw this in like an oven. Yeah, but you wouldn't have to, it wouldn't be like 450 or 350. It would be, what's that in Celsius? Might be like 300. Less than 300 degrees, less than 300 degrees, maybe like 250 or 275, something like that. So yeah, the can would explode. Hairspray, be careful with that stuff. Okay, so those are the kinds of questions that you're going to have, and you're going to find them on page 3. Sorry about the bell. You're also going to find them on page 4, but you don't have to do page 4 yet because it also has the ideal gas law. This was like a combined gas law. We're going to get to the ideal gas law next. So for right now, pages 1, 2, and 3, you should be able to do no problem. And maybe some of page 4. See if you recognize how to do any of that. But we'll officially do page 4 after the next set of notes. Thank you all.